All right, so now what I told you about this game, um, and I told you about the game in terms of maintaining a loop invariant, but um, and this is a standard way of teaching it. But let's just for fun look at a second proof using the game, and maybe you'll find this um, less intuitive than the loop invariant. Maybe you'll find it more intuitive than loop invariant. Either way, it'll just take a few minutes, and we will show what we're going to do. Right. So what we're going to do is we're going to take some greedy algorithm for some computational problem P. And what's the definition of a greedy algorithm? Is that the algorithm chooses locally optimal choices, ignoring long-term consequences. That's the definition of a greedy algorithm. And what do we want? We want to prove that on every input, the algorithm finds some solution, right? SA is the solution returned by the algorithm. The algorithm finds some solution, which is an optimal solution for input I for problem P, right? That's what our goal. And what does it mean, an optimal solution? Of the solution that, right, the value slash cost of the solution returned by the algorithm is at least as good as every other valid solution for this input, right? That's the definition of what we want. And our goal is to prove that if you have this, then you get this. But clearly that's not always the case because most computational problems do not have working greedy algorithms. All right. Why not? Because they make decisions ignoring long-term consequences. But our job is to consider problems in which they do have um, optimal solutions. So how do we do that? I'm going to define a new concept, which is right. I said before that when the algorithm just chooses a lion, we can't know whether that's globally optimal, whether that's a good thing to do so far. But I am going to define a concept of a globally optimal step, what it means that taking a line is a globally optimal step. And the way we're going to do it is we're going to say, what is the potential value that an algorithm might obtain, given that it's committed to the steps AT or AT minus one? What is the best it could do in obtaining a full solution? And we want to see that the best it could do doesn't go down, it doesn't get worse when the algorithm makes this next choice. So to more formalize this, suppose we know what the algorithm has done so far. We want to say, given the algorithm is committed to this, let's look at all solutions that are consistent with what the algorithm has done. And let's take the value of the best solution that's consistent with the algorithm done. So maybe what the algorithm has done so far is really stupid. And so now then this value would be lower. And what we're saying up here is, even if what we did in the past was stupid, the step you take next doesn't narrow down your possible solutions down such that the best you can do gets worse. All right, so that's what we're going to define to be a globally optimal step, and we're saying that if the algorithm does that every time step makes a globally optimal step, then the algorithm will return an optimal solution. And this is an easy proof, which we can give, and we'll give in a minute. All right, so let's go over and talk about our game, remember we said we defined a game which was this sort of solution switching game, and your job is to prove that the prover can win that game. And so if he can win this game, what does that tell us? That here's a first order logic statement which defines what it means for him to win the game. It means for anything the algorithm has done so far in any solution that the fairy godmother might have, there exists a way for the prover to come up with a solution that's still consistent with what the algorithm has done and whose value is at least as good as it was before. All right, so that's a logic, first order logic statement to prove that states that we can win this game, and we're going to prove that if this first order logic statement is true, then the potential value doesn't go down, right? And hence the algorithm works. All right, so in 1090, I talk about how to think about first order logic statements as a game. And you can imagine that the game for this first order logic statement is the game that we talked about. And we'll talk about that in a minute. All right, so your job is then to prove that the prover can win this game, in which case we're done. All right, so let's start backward. Let's start again with this step here. So let's assume that we have this, that each step the algorithm makes is globally optimal, and we'll prove that the algorithm returns an optimal solution. So to do that, let this sequence be all the actions taken by the algorithm from the beginning until the end. And remember, AT is the actions, all the actions that the algorithm has taken up until time t minus up until time t. And what we're claiming is that we have this definition. So if we have the statement here with this equality here, then bang, we can just write that all of these guys here have the exact same potential value, right? That's the statement that we have, that we can use. All right, let's go to, again, it's sort of establishing the loop invariant, right? It's at the beginning. What is the potential value at the beginning? What's the potential value at the beginning? The algorithm A0 hasn't made any choices whatsoever. So every solution is consistent with, extends what the algorithm has done at the beginning, because the algorithm hasn't done anything at the beginning. And if we look at the definition of the potential value, it's what's the value of the maximum solution consistent with what the algorithm has done. Well, every solution is consistent with what the algorithm done. So this is just equal to the maximum value of a solution, right? Because we're considering this maximization is over all possible solutions. All right, let's now go over to the other side. At the end, the algorithm has committed to a particular solution, right? If the algorithm is done, it has a solution. And so what are we maximizing over? Well, there's only this one solution that the algorithm has fixed. And so we're maximizing over one solution. And so what does this equal? This equals the value of the solution that the algorithm returns. Right? And then you see this gives us what we want, right? Because it shows you that the value of that the algorithm returns is actually equal to the value of the maximum solution, right? And that completes that proof. All right, so let's go back to our first order logic statement. We want to prove that if we have the first order logic statement, then these potential values don't get worse. All right, that's what we're going to prove. We're going to slide it over so we have a little bit more space to work with. And we're going to assume that we know that this first order logic statement is true. Well, If you took 1090 from me, then you'll know that when you know a statement is true, right? Here we're assuming it's true, then we can pretend that we have an oracle that can win the following game for us, right? What will the oracle? The oracle is going to assure us that this first order logic statement is true. And if she's assuring us, then what can we do with that? Well, suppose an oracle assures you that something is true for every object X. If it's true for every object X, then I can specify my favorite object X, and she'll assure me it's true for that one, right? Now, suppose she's assuring me that something exists. Well, if she assures me it exists, that some Y exists, then she can construct Y for me and then assure me it's true for that Y, right? And what are we assuring? We're assuring this statement at the end here. So that's what the oracle will do for us. All right, so let's do that in this case, right? So the oracle is assuring us that something is true for all of these things. So what are we going to give her? We're going to say, hey, oracle, if it's true for all of these things, then it's true for what? Well, the input, right? We're considering a particular input and wanting to know what the algorithm does on that input. And we're going to give her the input that we're considering. And we're considering proving that AT minus 1, AT has the same potential value as AT minus 1, right? So we have a particular AT in mind. So those are those values that the algorithm has done is what we're going to give her, right? And she's also claiming that something works for every solution that the fairy godmother might be having, right? Which solution we'll give? Well, what's the definition of the potential here over here? What's the definition of the potential value of what the algorithm has done? Well, it's the best over all solutions that are consistent with that, right? So we're going to let ST minus 1 be the solution that maximizes those solutions that are consistent with AT minus 1, right? And that tells us that the value of ST minus 1 is actually equal to, right, this maximum, right? And so we're going to take this line and we're going to write it down again because it's going to be useful, right? Here we have this statement. All right, good. We had the for all, and we gave these various objects to our oracle, and she assures us that the statement is true for those objects. And then what does the fairy godmother, what does the oracle do? The oracle says, hey, actually, there exists some ST. So she's going to give us the solution ST that we claim to exist, right? And what are we going to do with this ST? And what's true about this ST? Well, it's at least as good as the ST minus 1. All right, so if ST minus, so here we have ST is at least as good as ST minus 1, right? So there's another statement which we can write down over here. All right, now we need one more statement, right? We need to get it over to the potential value of ST. Well, the potential value the potential value of AT, the potential value of AT is the maximum over all things extending, all solutions extending AT. And here we have some solution extending AT. So the maximum of all that extend AT are going to be at least as big as this value. So that gives us that the potential value doesn't go down, right? Which is really the direction that matters to us. So we've done one direction. Just to complete the proof that we got the other direction as well, in case you want it. We don't need it. We don't actually need it for the proof, but in case we do, as the algorithm commits to more and more things, it narrows down the set of solutions that are consistent to it. So we're taking this maximization over fewer and fewer solutions. And so the maximum can't go up. The maximum can at most go down, right? So your potential value can never go up as you make more and more restrictions. You can only go down. And that gives us our equality. And we're done, right? Does that make sense? All right, so let's go back to everything. And that proves that if we have this first order logic statement, then we get that the potential value doesn't go down, and then we get that our algorithm is optimal. So let's go back to understanding this first order logic statement. We need to prove it, right? Before we had a fairy godmother who assured it was true, but now we're trying to prove this. And in 1090, I talk about how proving a first order logic game is equivalent to coming up with a strategy for the following game, right? If you want to prove that something is true for all x, the way you do it is you have an adversary presents you some worst case x. In a proof, you might say, I want to prove for all x, so let x be an arbitrary object, and then go ahead and prove it for x. But I like to have it more personal, so I'll say, let x be an arbitrary object given to me by some adversary, right? So here the adversary is providing all of these objects. And then we have to prove there exists something. Well, if you want to prove that some y exists, the way the prover does that is because it's constructing a good y, right? So the prover has to construct the S T, so that, right, that's our job there. And what does it mean to have a good, the prover wins if the solution obtained is at least as good, right? So this is the game I taught in 1090 to relate to this first order logic statement, right? Does that make sense? All right, but you might remember the game has different players, right? But I just changed the players to make it a more friendly story, right? Instead of having the adversary providing these objects, we have the algorithm and the fairy godmother providing them. But our job really is given those objects given to us by these players. The prover's job is to be able to produce ST. Right? Does that make sense? And we've done all these parts, and the part that you will do to focus on is the game. And that's what we're going to do for the rest of the section. And that's all I have to say. All right. Bye, everybody. I hope this one recorded.